Hello students, in this video I will be talking about particle nature of light. In my last video I had discussed about interference and diffraction, which were only explained on the basis of wave nature of light. But wave nature of light cannot explain certain observations like blackbody radiation, photoelectric effect, variation of heat capacity with temperature, and line spectra of an atom. In this video, I will only be focusing on blackbody radiation. To understand blackbody and the radiation, we will have to first of all know the definition of a blackbody. A blackbody, I will write it down. It is an ideal body that can emit and absorb electromagnetic radiations of all frequencies uniformly. Now here, this part is very important. All frequencies uniformly. As it is said that it can emit and absorb radiations of all frequencies uniformly, it means that they are good radiators as well. Now, since they are good radiators also, they absorb and emit radiations of same amount of energy per unit area. Now, since it can emit and absorb same amount of energy per unit area, it is in thermal equilibrium with its surrounding. Thermal equilibrium with its surrounding. Its surrounding. So what does this statement mean? It means that it is emitting and it is absorbing radiation at the same rate. But you also have to focus on this part, ideal. In real life, there is no object which can perfectly do this. So no object is ideally a black body. Normally what happens? So we will see what happens normally. Any object, suppose this is an object. Any object, when a radiation is emitted, is incident on that object, there are three possibilities. This is the incident radiations on the object. A part of it is reflected. A part of it is transmitted. That means passes through it. And a part of it is absorbed. So, in practical life or in real situation, these three phenomena take place whenever light is incident or radiation is incident on an object. Reflection, absorption and transmission. It cannot absorb and emit radiations of all frequencies uniformly. So no body is actually a black body. So then what happens? Two substances, carbon black is considered to be very close to a black body behavior. Otherwise, we can have a cavity. Suppose we have got a cavity with a very fine hole in it, and when light enters through this cavity, enters to the cavity through this fine hole, it strikes, it is incident on the inner surface and gets reflected internally. So you can say that such type of a cavity can be approximately close to a black body, but there is no object or body which can perfectly behave like a black body, and black body radiations are only a theoretical concept. Now we will see that even hot objects emit radiations. We are going to talk about hot objects and how do they emit radiations. There is a common observation that when we heat an iron object, first it becomes dull red and gradually it becomes deep red as the temperature increases. So when we heat iron object to even still higher temperature, I am going to discuss what happens. It first becomes dull red, and as temperature increases, it becomes deep red. On further increasing the temperature, it emits white light, white in color, and finally to blue color. So what does this observation tell us? You remember Vibgyor? As we are moving from red end to the blue end, the wavelength is becoming shorter. That means as the temperature increases, energy of higher frequency and shorter wavelength is emitted. And at a particular temperature, red light was intense, and at another temperature, blue light was intense. That means at a particular temperature, red light is intense, and at another temperature, blue light is intense. So what does it show? It shows that every color has a maximum at a particular temperature. That means at different temperatures, different wavelengths have their maximum intensity. So let us focus on this part now. We are going to study the relationship between wavelength and intensity of light emitted from an hot. Now we will talk about intensity versus wavelength graph. We will see what is the relationship between intensity and wavelength of light emitted. So you have the graph in front of you. You can see there are two curves at T1 and T2, and T2 is more than T1. So when we minutely observe the graph, the curve, we see that the intensity of emitted radiation of an hot object increases with increase in wavelength. You can see that the wavelength increases. On x-axis I have taken the wavelength, and the y I have taken the intensity. And as intensity of light emitted increases, it increases with the increase in wavelength of light. It reaches a maximum. That means at this point the intensity of emitted radiation is maximum, and gradually it starts decreasing with increase in wavelength. So as wavelength will increase, the intensity of the emitted light will start decreasing after reaching its maximum. Another point to be noted over here is that the maxima of the curve, you can see we have got the maxima of curve for T1, and this is the maxima of the curve for T2. The maxima of curve shifts towards shorter wavelength as the temperature increases. So as we increase the temperature from T1 to T2, the maxima of the curve shifted towards the shorter wavelength. That means If we increase the temperature, the graph will not be smooth. So we'll write down the observations of the graph. The first is that the intensity of emitted radiation increases with wavelength. Reaches maximum and then starts decreasing, and then decreases with wavelength. This is the first observation. The second observation is that as temperature increases, the maxima of a curve shifts towards shorter wavelength. It shifts towards shorter wavelength, as is the observation. This graph is also given in your book. You can refer to that figure. So as the temperature increased at temperature T2, the maxima of the curve shifted towards shorter wavelength. So these are the two main observations of the graph, which shows the relationship between intensity and wavelength. But this intensity and wavelength relationship, upon several attempts, could not be explained on the basis of wave nature of light. No matter how many attempts were made, but scientists were not able to give a valid explanation to the relationship between intensity and wavelength on the basis of wave nature of light. Then came Max Planck, and Max Planck made certain assumptions, and he assumed that the surface of the radiator or the object is composed of atoms, and these atoms behave as oscillators. So what is an oscillator? That oscillates. What is oscillation? To and fro motion is called oscillation. So the atoms which are present on the surface of the object, they behave as oscillators, and when they interact with electromagnetic radiation, then the frequencies of the oscillation change. This was the assumption made by Max Planck. Max Planck also said that electromagnetic radiations, the energy of electromagnetic radiation is not available continuously. It's not flowing continuously, but is available in discrete chunks. That means in small parts having certain amount of energy. So let's focus on that part now, and this is what forms the basis of quantum theory. That energy of electromagnetic radiation is quantized. It is not continuous but available in small packets. So Max Planck said that energy of electromagnetic radiation is directly proportional to its frequency. Higher the frequency, more is the energy of the radiation, and vice versa. So when you remove this proportionality sign with equality, he introduced a constant of proportion which he called Planck's constant. So this was the relationship that he had developed, and the value of H is 6.626 into 10 to the power minus 34 joule second. This is the value of Planck's constant, and he also said that energy does not flow continuously, rather it is an integral multiple of a whole number n, where n is equal to 0, 1, 2, 3 and likewise. It shows the quantization of energy. Now quantization of energy means energy of electromagnetic radiation is not continuous, but it is available in small packets, and these small packets of energy he called as photon. Now what will be the energy now when we substitute the value of n as 0, it would be either 0, it can either be h nu, or it can be 2h nu, 3h nu, and likewise. So you cannot have energies anything in between them. You cannot have energy between h nu and 2h nu, or you cannot have it between 2h nu and 3h nu. So this is what quantization of energy concept is. And the smallest energy that can be emitted or absorbed by any substance is known as quantum. He called the smallest energy emitted or absorbed. The smallest value of energy emitted or absorbed is called quantum. So what is a quantum? Quantum is the smallest value of energy absorbed or emitted. So this is the quantum theory of radiation as proposed by Max Planck. Now if you have any difficulty in assuming that what do we mean by continuous flow of energy or flow of energy in small packets or discrete value, so you can assume that suppose if you are watering a plant or a field, you can do it in two ways. Either you use a hose pipe to supply water, or you can use a bucket and mug. So when you supply water using a hose pipe, the flow of water is continuous. But when you use a bucket and mug to water a plant, the flow of water is in small packets, and that packet will be equal to the size of the mug that you are using. So when you take out water from the bucket using a mug, then you are supplying water in small definite quantity. So that becomes a discontinuous flow of water. But when you are supplying water with the help of a hose pipe, that becomes a continuous flow of water. So Max Planck said that flow of energy, that means energy is neither emitted or absorbed continuously, but it takes place in small packets. And this is what quantization of energy is. So I hope you are able to understand what a black body is, how do normal objects behave, how different they are from black body, and what is quantum theory of light. So Max Planck had sown the seed for modern physics. This concept could not be explained on the basis of classical mechanics or wave nature of light, but these facts could only be explained on the basis of particle nature of light. So when we will talk about photoelectric effect, it will be clear that there are two ways that light behaves. One is like a wave and another is like a particle. So whenever light propagates, it behaves like a wave, but when it interacts with matter, it behaves like a particle. So in my next video, I will be focusing on photoelectric effect. Thank you.